I know this is going to be really weird because it's now 10 till 7 on Monday evening. You guys are going to be watching this tomorrow morning right after I walk out the door. So it's just a little bit weird. Anyway, just stick with me. So what we're going to do is work through this sheet. There's these 3 problems. So this is kind of like a summary of everything that you have done in terms of the equations. So let's just start with the big equations. Chloe pause. Focus. Okay, 3. Count them. 3. So you have little g equals big G mass over r squared. Now remember, listen to me. Listen to me. Okay? Emma Hayes, right? Listen. That is not the mass of what is falling. That is the mass of what you're falling towards, okay? The Earth, the Moon, Mars, whatever that is, okay? This is why little g is not dependent upon what is falling. Little g is only dependent upon the mass of the object and how far you are from the center. So then you've also got little v equals big G, mass of the Earth over r, and then that is the square root of that, okay? Again, notice what is missing. Emma Hayes, your mass is not there, okay? No one's is. Don't take it personally. No one's is. Well, Grill is gone, okay? Bethany, your mass will cancel out. It's all the same. So here's what you've got. Then you've got what are called the Swiss Army knife, which is big G m t squared equals 4 pi squared r cubed, okay? This is the pirate's favorite equation, r cubed, r maybe, okay? So not only is it an r, but it's an r cubed. So these 3 will allow you to solve any planetary motion problem, okay? So a couple words of advice. This r is always from the center out. It is never from the surface, okay? It is always from the surface out. So here's what we're going to do. We're going to work this first problem. So you got the planet, and you're told that the satellite is 122 kilometers above the Earth, and you want to determine the velocity and period of the satellite. So if you remember from yesterday, okay, Zach, I'm assuming you do. If you're not, this is somebody else answer. But what is the order of magnitude of both the orbital period in seconds and the velocity in terms of meters per second? Dramatic pause. Hopefully Zach has said they're both going to be 10 to the third. This is really weird teaching to an empty classroom and asking you guys students, but say let's try to make it a little more appealing and a little bit more alive. So when you get done, this velocity has to be 10 to the third, the orbital period has to be 10 to the third seconds. So if you want to do the velocity first, okay, cool. Big G, mass of the Earth over r, okay? It isn't squared. It's a common mistake that's made. It is not squared. It's just r, okay? Now, if you want to get fancy, if you really want to get fancy, if you wanted to be efficient, a lot of times you're multiplying big G times the mass of the Earth. So if you wanted to save yourself the hassle of hitting like alpha G and alpha M, you can multiply those 2 numbers together and store that as like a third variable, like call it, I don't care, H, I don't pick a number, pick a value. That way you can just do the recall of big G times M. Some would call that being efficient. Some would call it, you're kind of lazy, like you can't hit like alpha G times alpha M. But if you really just want to be efficient, it could save you some steps. Now, here's what you're going to do wrong, okay? Here's what you're going to do wrong. At this point, you all kind of know where this song is going to go. You know that you're told that this is 122 kilometers. So Olivia is sitting over there going, Mr. here's what I'm going to say, and she knows this. You're going to leave that as kilometers, and you're going to put it in there, and it's going to be an absolute train wreck, because you're going to get a velocity faster than the speed of light, which is bad. So then you go, oh, Mr. Burkamp, I'm not going to fall for your evil tricks, okay? Calvin is back there in the back going, I'm not falling for this, Burkamp. So Calvin is going to go, hey, I'm going to convert that into meters. Cool, okay? All right, so we got that part of it right. Now, Maddie's over here going, no, still bad, still bad. So remember, that distance has to be from the center of the Earth out to that orbital satellite. So this needs to be big G, mass of the Earth, over 122,000 meters, plus the radius of the Earth. Now, if you do this, when you take the 122,000, okay, I guarantee you, I'm not here, but I guarantee you, Rylan is crunching these numbers if she hasn't already. When you do this, and you don't have to rewrite big G mass of the Earth each time. If you're hardcore and you really want to, that's cool. Okay? I'm really tired, by the way. So, it's been a long day. So, the other thing you can do, and now my voice is beginning to fail. Oh, it's a good day. So, when you add these, do not round that number, okay? You keep all of the digits. Do not round it. So, if you don't round it, which you're not going to, you get 6493600 meters. Okay? Now, if you go through the order of exponents, so this is 1, 2, 3, 4, 5, 6. This is 10 to the 6th. Okay? And Chloe Pauls, I know, is our exponent expert. And that's 10 to the minus 11, and that's 10 to the 24th. So she's going, oh, Burkamp, I got you. So 10 to the negative 11 times 10 to the 24th gets you 10 to the 13th. 10 to the 13th divided by 10 to the 6th gets you about 10 to the 7th. You take the square root of that, oddly enough, you're going to get 10 to the 3rd. Make sure everybody can do this calculation, okay? Trust me, don't just rely on Rylan to do it, okay? Because on the test, I guarantee you, you can't go, hey, Rylan, what'd you get from this answer? I'm not sure my answer. No, okay? No, bad. So anyway, if you do this, you get 7,840 meters per second. And that matches what we said. Hey, it should be something times 10 to the 3rd, which is cool. And then it's slightly less than the 8,000 meters per second, which is what you would have exactly at the Earth's surface. So we're a little bit above the Earth's surface. The answer is a little bit less than 8,000. Hey, it goes like we thought it should. Okay. Now you need to find the orbital period. So this is you're going to start with this big Swiss Army knife. Big G m t squared equals 4 pi squared r cubed. Okay? You have to be fluent in solving this equation for either mass, period, or radius. Okay? You have to be absolutely fluid in this. So, here's what you got. In this case, you want to solve this for t. So divide by big G, mass of the Earth, and then take the square root of that. Don't forget that pi is squared. So at this point, you have a decision to make. If you want to get rid of that square root and make that 2 pi times r cubed over big G, mass of the Earth, that's cool. If you want to leave it underneath the radical, I don't care. This is completely and totally up to you. Okay? It's however you want to play the game. Anyway, so if you do all this, you get, and again, you're going to use the same radius that you had up here. Okay? It's the exact same radius. It still has to be from the center of the Earth out to that satellite. Okay? It still has to be the exact same thing. So if you do this, crunch all the numbers, you get 5,210 seconds, which is to the 3rd, which is cool. That's what we said it was going to be. Which is about 88 minutes, which is about an hour and a half. So like the International Space Station, near Earth satellites, about an hour and a half. Okay? 10 to the 3rd. There you go. Okay, now we need to calculate the centrifugal acceleration. And we know this thing is undergoing centrifugal acceleration because if it wasn't, it wouldn't be in orbit around the Earth. So by virtue of the fact that we live on a round rock, so this is what we talked about yesterday. When something's in orbit, it is not in zero gravity. You cannot orbit in zero gravity. What's happening is that you're just in a continuous state of free fall as it goes around the Earth. So there's a couple ways you can calculate centripetal acceleration. You could use 4 pi squared r over t squared, okay? Or you could use v squared over r. Personally, I did the v squared over r because that was a little bit simpler, okay? You didn't have to deal with the 4 pi's. You're going to get the same answer either way. So if you do this, you get 9.46 meters per second squared, okay? Look at the orbital velocity of the satellite, and then you divide by, again, the same radius, okay? It is not a different radius. It's still the same radius from the center of the Earth out to that satellite. It's the same radius we've been using, okay? Now, hopefully that makes sense. So, because of the fact that you're undergoing centripetal acceleration, okay, it's a cool thing. You got your velocity. If you look at this in terms of order of magnitude, your velocity is like 10 to the third, but that's going to get squared, which Chloe Pauls will attest that that's 10 to the sixth. And then you divide that by that radius, which is 10 to the sixth. Hey, you get 10 to the 0. Ooh, kind of makes sense. Okay. Now, here's the next thing. We need to calculate little g. Now, if you think this through and visualize this, imagine, if you will, we've got our Earth. And we're going to build a really, 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 really tall tower. That's 120 kilometers tall. Hey, it's really, 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 really tall. And you're going to climb up this ladder, okay? Right? Climb up the ladder. And you're going to get up there, and you're going to drop this ball. Now, if you think this through, you got to figure that when you drop it, the value of little g, which is your gravitational acceleration, is going to be less than 9.8 meters per second squared. Because if I drop it here, oh, that's 9.8 meters per second squared. If I climb all the way to the top of the tower, where I'm 120 kilometers is about 50 miles, okay, ish. So you're about 50 miles above the surface of the Earth. You got to figure little g is going to be less than 9.8 meters per second squared. It's certainly not going to be 0 because you couldn't orbit if it was 0. So we're going to use big G, mass of the Earth, over r squared. That mass is not the mass of the bowling ball or the golf ball or the box of chocolates, whatever it is that you drop. Okay? It's the mass of the Earth. Now, if you put in the actual radius of the Earth, 6.3713 times 10 to the 6 meters, you generate 9.8 meters per second squared. But we're 120 kilometers above the Earth. So this has to be less than 9.8 meters per second squared. Now, wait for it, drum roll please. Oh, how cool is this? You get, shockingly, the exact same answer. Okay? Stunning as that may be. You get the exact same answer. Now, coincidence? I think not. These answers have to be the same, because the short version of this is that your gravitational force is what's creating your centripetal force. Oh, that's the mass. Now we're back to Emma Hayes. We're back to you, Emma. Mass of Emma Hayes times G equals the mass of Emma Hayes times her centripetal acceleration. Cool. This is just a simple mass times centripetal acceleration. Emma Hayes, I know I told you yesterday. It'll be yesterday for you, but it's still today for me, but you get the point. So you're going to drop out of the equation. Sorry, you do. So what you're left with is little g equals your centripetal acceleration. Oh, how cool is that? But it has to be that way because your gravitational acceleration is what's creating your centripetal acceleration. Those numbers have to be the same because gravity is what's keeping you in orbit. Okay, so on the test, and I promise you I'm going to ask you this question. I'm going to ask you to calculate the centripetal acceleration of a satellite as it goes around the Earth. There's two ways you can do it. You can find the centripetal acceleration. You can use 4 pi squared r over t squared. You can use v squared over r. Or you could find what little g is at that altitude above the Earth. I don't care. They're all going to be the same. So I promise you, it's going to be the last problem on the test. I will even tell you where it is. It's going to be the last problem on the test. Little g equals your centripetal acceleration. And that centripetal acceleration could either be v squared over r, or 4 pi squared r over t squared, or you can just find little g equaling big GM over r squared. Okay? Infomercial. But wait, there's more. Additional shipping and handling. Centripetal acceleration, little g. Don't care how you calculate it, they're all the same. Okay, now let's talk about the second problem. So you got a newly discovered planet, has a moon with an orbital period of 20.5 hours and a radius of 3.68 times. What is the mass of the planet? So this is how we do planetary motion. This is what we do, is that we make observations, say, of like Saturn. Saturn has a moon. Okay, maybe my moon. Doesn't make any difference which one. But you're going to pick a moon of Saturn. And you're going to go, oh, great. So if we can make observations about the moon, how long it takes to go around, and how far away it is, oh, great. We can find the mass of the planet that it's orbiting. So you're going to start with the Swiss Army knife. Big G M t squared equals 4 pi squared r cubed. This is where you have to be fluent. So we're going to solve this for mass. So I've got 4 pi squared r cubed divided by g t squared. So this is understanding the clues. So I tell you that it has a radius of 3.68 times 10 to the 6th meters. So notice that is not the distance above the planet, like the first problem was. I'm telling you straight up, that is the distance, okay? From the center of the planet out to that moon. You don't have to do anything. You don't have to add anything. Straight up, that's the number. Did you a solid, okay? All right, Addison, did you a solid. You don't have to add anything. Just boom, it's the number. Cool, got it. So, that's just the number. Now, you're also told that it has an orbital period of 20.5 hours. I am a jerk, I admit it. What you're going to do wrong, and you sit here and you tell the TV screen, because I'm on my way to Bueller, but you tell the TV screen, Mr. Burkamp, we won't do that. And I'm still telling you, on my way to Bueller, you lie. You're going to leave that as 20.5 hours. And you sit there and you go, Mr. Burkamp, don't be silly. Yes, this is what you're going to do. But you got to take the 20.5 hours and go, oh, 1 hour. That's 3,600 seconds. So that's going to go there. When you do this conversion, do not round this number. You keep all of those digits in the seconds. So you're going to have 4 pi squared. You don't have to do anything with the radius. You play that straight up. 3.68 times 10 to the 6th meters, and that's going to get cubed, divided by big G, and then if you do that conversion, you get 73,800 seconds. But now, here's what you're going to do wrong. Okay? Been there, seen it. You're going to forget to square the value of seconds. That's what you're going to do. You are going to forget to square that value. Okay? You're going to be so happy. It's like, oh, Mr. Burkamp, you didn't catch me with your evil trick. I converted that into seconds. Beautiful. Josiah, you converted it into seconds. Fantastic. Well done. But then what's going to happen is that you're going to forget to square it. Okay? Promise you. That's what you're going to do. Okay? William at this point is probably going, Mr. Burkamp, I don't know. Trust me, William. You're going to forget to square it. It's going to happen. Okay? Just not you, William, but this is in general what's going to happen. Anyway, so if you do this, you get 5.416 times 10 to the 21st kilograms. Cool. Lovely. Got it. Okay. Now, and this is how you do planetary motion. This is how you find masses of planets. You make observations about a moon. How long does it take? Get an idea of the radius. Boom, find the mass of the planet. Okay, on the third problem. This one. So this one, you have the moon has a radius of 1.4 times 10 with gravitational acceleration 1.22. What's the mass of the moon? So you're going to start with little g, which I always thought if I ever quit teaching and became like a rapper, which would be a no money making situation. But that would be my that would be like my rapper name, Little G. You know, give it up for Little G. Yeah. So he paused. You laughed at that. I know you did. Okay. So I got little g, big G, mass of the moon over r squared. Okay? So we're trying to find the mass of the moon. So we go grrr squared, it's like the dog pirate. We're going to divide that by little g or big G, and then we're going to get the mass. So again, this 1.40 times 10 to the 5th meters, that is the straight up distance. That is not the distance above, that is the straight up distance. So you've got the little g, which is 1.22 meters per second squared, times your radius, which is 1.40 times 10 to the 5th meters. Don't forget to square that, and then I'm going to divide by big G, and you get 3.58 times 10 to the 20th kilograms. Cool. Now we have the mass of the moon. Now this is where I'm trying to get you think a little bit deeper. So what I'm asking on the next question is that if you happen to have a 1 kilogram mass, this is a half a kilogram, just to get the idea. This is a 1 kilogram mass. What I want to know is how far from the center of the moon do I have to get so that this weighs exactly 1 Newton? So if you think about this, I'm going, oh, okay, right. If I have a 1 kilogram mass and I want it to weigh 1 Newton, and that's times G, check my math. If I take 1 and divide it by 1 kilogram, I get 1 meter per second squared. Right? So what I want to know is, imagine this is the moon. And you're going to move this thing at some height above the surface so that when you drop it, instead of falling at 1.22 meters per second squared, which it is when you're on the surface, you're going to drop it, and so it accelerates at 1 meter per second squared. Okay, that's going to be the difference. So you're going to go back to little g equaling big G mass of the moon over r squared. Now, at this point, you have to solve for r, so this gets a little sketchy. Okay, it's not bad though. So I got grr squared equals big G mass of the moon, and then I want to find that radius, so I'm going to divide by little g, and then I'm going to take the square root of that to get little r. So I've got little r That could be the name of my dog. Give it up for little g and little r. Or maybe I get like a short like pirate to hang out with me. Like give it up for little r. Anyway, it's now 7:15 and I haven't eaten, so I'm a little bit punchy. So I got big G. You have to use the mass of the moon, which we just found to be 3.58, times 10 to the 20th kilograms, divided by 1 meter per second squared. And if you do this, you get 1.55 times 10 to the 5th meters. Now, what you'll notice, oddly enough, is that this is greater than the radius of the planet itself, which we said was 1.40 times 10 to the 5th meters. So then that should make sense. Cool, right, Brookhamp. 1.40 times 10 to the 5th. That's at the surface of the planet. That's 1.22. I got to be a little bit above that, so that little g drops to 1 meter per second squared. Okay, if you can do those, you should feel relatively good about what's going to happen. So I'm going to step over here. I'm going to get the assignment so I can talk you through some of these problems. I'll be back. I'm not going anywhere. Okay, so yellow sheet. Kind of looks like a star. That's why I ran it off on yellow. So let's talk about even that first one. So you got the gravitational attraction between a 20 kilogram cannonball and a marble, separated center to center by 4 centimeters. Compute the mass of the marble. So imagine this. Here's the cannonball. There's the marble. So this is 20 kilograms. This is the mass of the marble. That's what you don't know. You know the distance that separates them, and you know the value of the force. So this is Isaac Newton's wheelhouse. So you're going to go, oh, F equals big G, the mass of the cannonball, times the mass of the marble, divided by distance squared. Now, and I know I've preached this to you before. You're running with the scientific big dogs at this point, okay? Do not go, it's just going to save you so much hassle. Solve this equation first. Don't put in the numbers and then rewrite all these numbers 2 or 3 times trying to solve the equation. Solve the equation first. Then put in the numbers. Pay attention to the units, okay? So that first answer with the mass of the marble should be on problem number 1, should be something times 10 to the minus second, okay? Just ballpark, pretty small marble. Now, on number 2, you have 2 identical spheres. They're identical. They are identical. And they're separated by 1.2 meters. They experience a gravitational force of 1 times 10 to the negative 4th. Compute the mass of each sphere. So oddly enough, you're going to start with that equation. You know the gravitational force. You know what big G is. You know how far apart they are. Solve for the mass. Now, this is where this gets tricky. M1 is going to equal one of the masses. But since they're identical, M2 is also going to equal the exact same mass. Now, Chloe Pauls, Miss Exponent. I'm going to multiply mass by mass. I'm not adding them. This is up Chloe Pauls' wheelhouse. I'm multiplying mass by mass. So do I get mass squared
Or do I get 2m? Hopefully everyone goes, oh, Mr. Hurricane, you get m squared. So this becomes m squared. Solve for that. When you get to number 3 is identical to that last problem that I worked on this sheet. The only difference is instead of g being 1 meter per second squared, little g is going to be 3 meters per second squared. So your answer to number 3 should be something times 10 to the 7th. Okay, it's going to be a big distance. And if you think about it, that distance has to be bigger than the radius of the Earth. Because if you're standing at the Earth, g is 9.8 meters per second squared. We want little g to be 3 meters per second squared. That's a long way out. Okay. When you get to number 5, 2 planets, Uranus and Neptune, they both have very long orbital periods because they're a long way from the Earth. You're trying to find the gravitational force between them. Pay attention to the units. I'm just telling you, pay attention to the units. You're just going to use F equals big G m12 over d squared. Let me explain what's happening on number 6. On number 6, once they figured out the structure of the atom, and these guys were all physicists, so they said, oh, the nucleus is going to be like the sun, and the electron is going to be like the Earth. Cool. This is something they could grasp because they had all studied planetary motion. So the first thing that's going to happen on number 6, you're going to calculate the gravitational attraction between a proton and an electron separated by 5.3 times 10 to the negative 11th, which is really small. So that first answer on A, on number 6, is going to be something times 10 to the negative 47th. It's going to be a really small number. So what they quickly figured out is that that's a cool model where you have an electron going around the proton like the Earth goes around the sun. But the gravitational force just isn't strong enough. So they said, okay, there's got to be something else. Okay, now because they have oppositely charged particles, there's also the electromagnetic force. And I just gave you that number. So on that one, you're going to compare them. So to get that one on number 6, take the bigger value, which is the electromagnetic force, divide that by 10 to the negative 47th, and that will tell you how many times greater that is. So the last thing I want you to do on C is say, okay, what would have to be the mass of the proton so that if you look at big G, mass of the proton, mass of the electron over distance squared. So you're going to say, okay, what would have to happen? How much mass would a proton have to have if a proton had mass? Actually, it does. It's just really small. But anyway, so to create the strong enough electrical or gravitational force to hold that electron in like orbit, that's going to be a big number. So that's like 10 to the 12th. So 6C is 10 to the 12th. So here's your sequence. On 6A, that's 10 to the negative 47th. 6B is like 10 to the 39th. Times greater, that's a big number. And C is going to be like 10 to the 12th. Okay. 7, 8, and 9 are all just your basic run-of-the-mill equations. When you get to number 10, leave like a half a page. I don't have time to explain number 10 today. So when you get to number 10, leave a half a page. We're going to work number 10, which is going to be really weird, which is going to be tomorrow for you guys, which is 2 days for me, 2 days from today for me, which is going to be Wednesday, okay? So don't worry about it. It's the bronze points. It's cool. I just don't have the time to explain all that right now. When you get to number 12 and you're finding the mass of Saturn, that should be something times 10 to the 26th. So number 12 is 10 to the 26th. Okay? Now, let's talk about number 13. So one of the things that makes your life functional right now in terms of where you are, so that you can track where everybody else is and you know, and your GPS system works, is that we have a satellite, a parking lot of satellites that orbit above the Earth, but they're always above the same point on the Earth. That's what allows us to have fixed points that you can triangulate where your phone is as it bounces these signals off the satellites. Now, the problem is that you have to park them way out so that they have a period of 24 hours. So the reason that you want a period of 24 hours is that as the Earth spins and takes 24 hours to spin on its axis, you want this to take 24 hours. So therefore, it's above the same point all the time. So, and at this point, they go, oh, I'm paranoid. There's satellites watching me all the time. There's so many. It's okay. Without it, your life would be different. Like, you would have to actually know directions on how to get home. It's like, oh, really? Yeah. Okay. So, on number 13, you're going to start with the Swiss Army knife equation, and you're going to know the period, which is 24 hours, which you're going to convert into seconds, hopefully. So you need to find the radius. Now, here's the deal. When you find that radius, that's from the center of the Earth out to that satellite. What I'm asking you for is how far above the Earth this thing is. So when you get the radius from 4 pi squared r cubed equaling big G mt squared, once you find that radius, that's from the center of the satellite to the center of the Earth. To get this, because this is what you want, you subtract out the radius of the Earth. Because if you think about it, your phone is not in the center of the Earth. Your phone is at the surface of the Earth. So the calculations on the transit time of the signal has to be based on that distance above the Earth. So you're going to find it from the center, but then you're going to subtract out the radius of the Earth. So the answer to number 13, after you subtract out the radius of the Earth, is still 10 to the 7th. So your answer to 13A is 10 to the 7th. That's even after you subtract out the radius of the Earth. Now, when you get to 14, okay, this is the International Space Station. And here's the contrast. Your answer to 14A should be something times 10 to the 5th. So on 14, to kind of give you some perspective, I asked you to compare the distance from Kansas City to Wichita, because that's kind of a number that you can reference. And the same thing is true on 13. Because everybody thinks these distances to the satellites are so big, okay? This just allows you to kind of put that number in perspective. 16 is old school. 16 is old school, that equation. V squared equals V naught squared plus 2AD. 16 is old school. I say again, old school. When you get to 18, 19, and 20, this escape velocity, and I'll give you more of a visual tomorrow. Basically, it's how fast you have to throw something so it doesn't return. So like if I take this golf ball and I throw it up slowly, it comes back down. If I throw it faster, it goes even farther. So the idea being is that if I throw it fast enough, it'll never come back. Okay, like it will leave the gravitational field of the Earth. So this is on your lecture notes. It is not on your equation sheet. What you need to use is V equals the square root of 2gm over r. The only difference between orbital velocity and this is that there's a 2 in front of it. So escape velocity, and I lay this out all on the lecture notes, is how fast you have to be moving to escape the gravitational field of the Earth, the Sun, whatever that is. Okay, I'm done. It is now 7:30. It's been a long day. I haven't eaten. I'm gonna get this uploaded. Thank you for participating as I talk to an empty room. I saw the janitor poke his head in and he was like, who is this madman talking to an empty room? Anyway, so hopefully that helped. If you have any questions, I'll get to those tomorrow. This assignment is due on Thursday, the day of the test, but we're gonna go over some stuff. Like I said, don't worry about number 10. I'll show you number 10 tomorrow. Okay, kids, you're on your own. Be free.